Our first lecture in this course, then we just want to set up some of the terminology and things that we use in statistics, and also define some notation. Some of you may have had another statistics course before. The notation might be slightly different, so we'll kind of so whether you've had another stat class or not, we'll get everybody started out on the same footing in terms of notation. Terminology. You have to do that regardless of what discipline it is. So with your fondness for statistics aside, we'd have to go through the terminology. If I were to take your biology course or your chemistry course, you'd expect me to learn the terminology there as well. So that's where we begin then here. Get all my stack set up. All right, when we collect data or a data set, we just have a collection of observed values for some defined set of objects. And so whenever we look at a data table or a data set, we measure several different variables here. Here I've just put those in columns labeled as variable 1 through variable m. And so that whenever we look at these, we could have an observation or object on which we're recording a measurement. And so we say that this is our observation 1 or object 1, and that we measure these capital M different things here, and this is referred to as a record. Okay. What I mean by these kinds of symbols here is that we're talking about numeric data. Data could also be character. Some references will refer to it as text or string. Most of the things we look at in this course then are numeric data. There are a few things, areas where we will talk about character data. Okay, so we have our first observation in row 1, our last observation then given down here in the last row, of course. All right, and so when we define a record contains a collection of responses for a single object or for a single observation. We define a population and a sample. So the population is the entire collection of objects of interest, and from that we select a sample. So the idea then is that we have this population, POP is my shorthand for population, and from this population of values then we make a selection. So we select our sample. Okay. We measure variables, either numeric or character, as we just talked about on the previous page. We may also refer to these as quantitative or qualitative variables. Examples then for numeric variables, we may be looking at things such as length or time. We have number of children. And of course, we could think of infinitely many possible things there. For character or qualitative variables, things that you may record or say are eye color. Could be your student classification. If a person is an undergraduate, are they freshman, sophomore, junior, or senior? At the graduate level, are you a master's, PhD, EDD, or vet? Among numeric variables, we can talk about discrete or continuous variables. And so discrete variable means that no finer or more precise measurement can be made. So if we wanted to think about what things that are discrete random variables, discrete variables, number of children, you either have 1 child or 2 or 3. You don't have 2.7 children. There's a finest measure that is achieved. Okay. Other things you might look at where you see things that occur in fractional values, shoe size. All right, you wear an 8 or an 8.5 or a 9. You don't have an 8.2. Okay, there's no finer measurement that you can have. And so typically then, if you're looking at surveys and you're measuring counts for opinions, so count data also classifies as discrete random variables. A continuous variable that you have all the values in a range or an interval are possible. And those length or distance, that first one I mentioned before on the numeric, is and most obviously a continuous measure. A length, you can, depending upon the tool you use, you can always get a finer measure, right? So that if you're measuring something that's small, whether you use a ruler like this with its graduations, or if you're using something that a caliper or micrometer, you can get a more, you're only limited by the precision of the instrument that's taking the measurements. Okay, other things such as time, weight or mass. Okay, if you have a more refined instrument, you can measure more exactly that. So that all those are things we would regard as continuous measures. So that's in addition. So we have numeric data, character data. Numeric can be discrete or continuous. Back out just in terms of all data. Okay, we can talk about 4 different categories or scales for any data. So whenever we look at the simplest is nominal scale, we're looking at labels for classes, and this nominal scale has the property of distinctness. Excuse me. And examples here, all the qualitative variables we were talking about. Okay, labels for different classes, if you had, say, yes-no survey data. All right, eye color. Okay, so it's not all qualitative variables necessarily, but here there's no order to things. They're just put in different groups. There's no way I can order eye color. Okay, one might think about in terms of, I don't know, color, try to assign some numeric values to colors, but really there's not a way to order eye color in general. It just determines different classes of individuals, right? Okay, your responses to a survey, yes or no, you just define 2 different groups. It's not putting any kind of order. It just says that we've just defined different groups. That's what nominal scale is. Okay, for a survey to be different, all of us have taken those things that are, do you agree, disagree, strongly agree. There's some order implied there. And so when we start looking at that kind of thing where there's an order implied, we actually move up a level to ordinal scale. All right, and so that if you were thinking the yes, no didn't have an order, well, your things we refer to as a Likert scale. And that's applicable to survey questions. Okay, the 1, 2, 3, 4, 5. The idea from strongly disagree or strong dissatisfaction, all the way up to strongly agree, those kinds of things. So what happens when you have an ordinal scale is you have all the properties of the classes above, distinct classes formed, but those classes now have an order. You can look at economic statuses if they're defined as high, medium, and low, those kinds of things. There's an order, or so we can just write any kind of a ranking of high, medium, and low. Classifications. We don't have a numeric value attached to that for magnitude, just different classes. By comparison, like I said, we know the very obvious definition here, high having certainly something in a greater amount than medium or low. Okay, so if we have also this distinctness and order, and now then we look at some equal differences between numbers reflect an equal magnitude among classes. We can have an arbitrary 0. All right, that's the next scale up. So notice this first bit here has everything the next lower scale had plus one more condition. Okay, and so examples here that we're looking at, equal differences may have an arbitrary 0 value. So where that occurs, we think when we measure, say, temperature, whether we're talking about Celsius or Fahrenheit. Okay, there is an arbitrary 0 in those. Of course, if you discuss what that scale means, not so arbitrary necessarily. All right, but we do have a 0 value. Okay, and the idea of a 10-degree difference is meaningful. Okay. Test scores. Okay, and depending upon how how precisely we can measure those, but the idea of a 0 value, just because you get a 0 on a test doesn't mean you are totally void of information, right? So I put that in as an interval scale. Okay, we move it up one more notch here. The last in the definition for scale is ratio scale. So it has all the properties of interval scale, which had all the properties of the two before it. And now then we have what means an absolute 0. So that a 0 means truly nothing. There's nothing, whatever this characteristic is, there is nothing here. All right. And so examples there would be those measures of, say, distance, and time. One could talk about temperature here on a Kelvin scale because there is an absolute 0. All right, but the idea here is that distance is, if something's 10 meters away from an object versus 20 meters, by having ratio scale data, that 20 versus 10, that means it's twice as, the distance is twice as far for the 20-meter object than it was for the 10-meter object. Now, when I look at temperatures up here, if I talk about 30 degrees versus 60 degrees on either of these scales, that doesn't mean that it's twice as warm at 60 degrees. Not when the concept of heat. That's not what that means. It's just an arbitrary way of measuring the temperature. So ratio scale, then that ratio, it's twice as large, it's 3 times as large. That ratio makes sense if you have an absolute 0. Okay? We can collect data on our samples or populations using either two types of studies. Observational studies, as we measure, observe the responses that occur naturally for the objects in the study. And so things that here, observational data is that if you take a survey data, things that naturally occur, I'm not imposing any condition. Stock market, weather, other environmental, Okay, we're not imposing a condition, we're just measuring what naturally occurs there, and we want to see if there's any pattern to or any differences. So it depends on our research questions there. Whiteout's not kicking up yet. Designed experiments. In these instances, we impose a treatment or impose some condition or multiple conditions and measure the responses as a result of that imposed condition. And so this happens, say, in pharmaceutical studies. All right, you have an active drug and a placebo, and you're trying to see if the active drug produces a better result, a better state of health than the placebo, or the lack of an active ingredient. Here at OSU, would guess be remiss to not acknowledge agricultural experiments. All right, the imposed condition can be either a variety of plant, a fertilizer condition, a pesticide condition, all right, versus, with and without, or some other level of a rate of application, okay? And so we see also these kinds of things then also in biological sciences. So the designed experiments where you typically look at a smaller group of individuals or objects, okay, because of this imposition of a treatment. Okay, so we're not limited, of course, to those, and each of these we could come up with several more things. Okay, everybody okay with that so far? When we have numeric data, the summary information can be calculated. Parameters. The definition of a parameter is the quantity that describes the population. Okay, so population parameters. And when we measure a summary statistic on when we measure a descriptive value for a sample, it's called a statistic. So define statistic without saying the word statistic was a little tricky there, wasn't it? All right, so statistics we compute on the sample, parameters are what are computed for the population. All right, so our challenge then is that oftentimes our populations are infinite or near infinite. It's not possible to measure the entire population. All right, so we want to be able to select a sample and based on sample statistics, draw some sort of an inference or make some sort of an estimation about what's going on in the population. Okay, our notation, then we look at capital N. Capital N is the size of the population. Okay, lowercase n is the sample size. Y with the subscript I. This I just refers to the ith observation. Of the variable capital Y. Some textbooks use X's, some use Y's, we use Y. When we have numeric data, then things that we can calculate, we talk about measures of central tendency to describe the middle of this data, whether it's sample or population. Where's the middle of this data, and how do we describe that? Okay, values that we can use then are referred to for numeric data as the mean or the median. And we'll get into the specific definition of these in just a little bit. We can also talk about the mode. We'll go through these three in detail. There are some other applications where we may talk about what's referred to as a harmonic mean. Or a geometric mean. So I mean over here by the term mean, is we'll see that later, it's referred to as an arithmetic mean. Measures of dispersion, how spread out is the data? Okay, so the simplest way we can think of that is what is the range of the data? What's the high score, what's the low score, and the range would be the difference between them. We talk about variance. or standard deviation. And when we get into the measures of dispersion lecture topic, we'll have a few more of those things that we'll go through. When we describe data, we oftentimes can construct a graph, or we're reading someone's graph they've constructed for us. And so a few of them that we'll talk about, I don't get into a lot of the details with them in this course. We can talk about box plots, stem and leaf display, histogram or bar chart, we also look at scatter plots, and we could have a whole course just on graphics alone. So we're going to have a brief little bit about graphics. Okay? All right, so going back through those then in more detail when we talk about measures of central tendency. So when we talk about a mean, we're referring to the arithmetic mean, or what you probably have known since the 3rd grade as an average. Okay? And so now then, using our notation, and how do we write that? Okay? So when we talk about a population mean, for the population mean is given by the Greek letter mu, lowercase mu. Okay? We take, and the summation, I equals 1 to capital N of the observations yi, and divide by capital N. So all this means, if you're new to the sigma notation, okay, all this means is that you're adding things up, beginning with I equals 1, that's y1 plus y2, all the way up to the last observation. The last observation would be y capital N. Okay, all divided by the number of things you added up, which was capital N. Okay, so if the sigma notation is new to you, that's all that it's doing. No, it doesn't matter.
On the I is equal to 1, that means we start at observation 1. Is that little I under the sigma?
Right. This I value here corresponds to this subscript here. So I equals 1, then you start with value y1, and then add up through y last, which is y capital N. Most usually for our course, the lower bound here will be at 1. There are some applications then when you get into more advanced statistical applications and areas outside of statistics where you wouldn't start necessarily at 1. Okay. For a sample, the notation is the capital Y with an over bar, and that's just pronounced as Y bar. Y bar then would take the summation from I equals 1 to lowercase n of the yi's. So it's still capital Y with subscript I. It's what the upper bound is capital N or lowercase n. We don't have a different symbol for the population of capital Y's versus a sample of capital Y's. Okay, there's not that distinction. But we add up all the things, the lowercase n values in the sample, and we divide by lowercase n. And so whenever we compute the mean, the mean is the algebraic center of the data. All right, so the idea then is that if you have a number line, let's say, here of all your different values for y, and so just the x's here kind of marking where our data occurs, you measure your value for y bar, everything is balanced about this data in terms of how far away each point is away from the mean. There's some balance that occurs there. Okay, we'll define that a little more specifically here in a bit. All right, whenever you see something as simple as consider the sample, it's a sample, it's not a population. So if you're going to compute anything, you're computing y bar. Okay, and so that all we're looking at here is if we consider the sample y equals 47139, we have a sample of size 5, and if we computed y bar, so very simply, that just, the summation then just says we're adding up the 5 observations and dividing by the number of observations. All right, so 12, 15, 24 over 5. So our y bar value is 4.8. You may also see a summary statistic in your textbook or on tests. If you just see something reported as the sum from I equals 1 to 5 here of the yi's, that just means what's the total, the grand total for the sample, or the if it's capital N, grand total for the population. So knowing the sample size, y bar, or the sum of the yi's is helpful. The second measure of central tendency is the median. When we talk about the median, that's 50% of the ordered data lie below this value and 50% are above the value. And so in order to compute the median, we have 2 steps. The first was we arrange the data in order. It doesn't matter really low to high, high to low, but I'll write it as here as low to high, as long as they're put in order. And then the second step is that we compute the median. Now, I've not come across any generally accepted notation for a median anywhere. People just call it what they call it. So this textbook has used lowercase m with subscript y, the median of random variable y. And this is written here for a sample. So we have a step function here. It's the lowercase n plus 1 over 2 score if n is odd. And it is the average of the n over 2 and the n plus 2 over 2 score. If the sample size is even. So again, our same sample as we had before was sample of size 5. All right. If we first order the data, okay, smallest observation being the 1, and so we have 1, 3, 4, 7, and 9. Okay. The position of the median is since odd is the sample size plus 1 divided by 2. Okay, so that means it's the third score. And so that would imply that our median is the third score in the list, which is 4. And if you have several, if some of your observations, say 4 occurs with a multiplicity greater than 1, that is that maybe you have 3 recordings of a 1, 2 recordings of a 3, 7 recordings of a 4, and so forth. You put all of those, not just and how many times they occur in that ordered list. Okay? If you had a sample that's an even size here, so here we have a sample of size 4, our ordered data would be 4, 5, 10, and 12. Okay, what is the position of the median? Or rather, we can just write M of Y is going to be the average of these two things right here in the middle. Agreed? So it's going to be 1/2, 5 plus 10. So the median doesn't have to be a value you've actually observed. Okay? If you're averaging between two scores. So this is the second and third. The second and third scores are averaged. Now, of course, for space and time here, I've only done very small samples. I save the hard ones for you. Okay, but so you have to put the data in order. So otherwise, if you, one of the most common mistakes on an exam, when I ask about a median, the most common mistake is to not order the data. So in this case, someone would report to me that the median is 11. Okay, because I forgot the basic thing first, put the data in order. Okay? I know that seems like an obvious thing, but in a test you can sometimes overlook a small detail, and I don't want you to do that. Okay? The median is much less sensitive to extreme scores than the mean. And so let's look at an example 1 here. Suppose my sample consists of values 1, 2, and 3. So here, the median is equal to 2, and the mean is equal to 2. Kept the math simple, right? In a second example, suppose my sample is 1, 2, and 96. Okay? Now when I look at the median is still 2, but the mean is, add up 1 plus 2 plus 96 is 99 divided by 3. So the mean is 33. So one extreme score can really affect the mean. All right? We tend to see, so whenever you're going to grad school because you've been attracted by the lucrative salary you're going to get when you finish, right? Okay? Because they tell you that, if you get this job, the average starting salary for people with this degree doing what you want to do is wonderful, right? That's what drew me into academia. All right? They tell you that the average score, average salary is and this nice figure, but when you start checking around, all of your work and whenever your investigation, nobody's making that kind of money. Well, why is that? Well, there's that one guy that got that job, or maybe there's a couple of guys. If we're looking at, they have those extreme scores, and so that mean is being inflated. So a better thing to look at was perhaps what's the median salary for people here, because now then that 1 or 2 guys or gals that got the really great jobs aren't totally misrepresenting what's going on here with the mean, right? All right, the mode is we report is the most frequently occurring response. Data sets can have a single mode, no mode, or be multimodal. Okay, and so that when we look at our original data set that we started with on the arithmetic mean, everything occurs once. And so whenever we look at this means to say that there's no mode. And I don't know of any symbol ever for a mode. So here, I see that 3 occurs twice, everything else occurs once. So in this case, for this sample, our mode is equal to 3. Now in this case, 4 occurs 3 times, 7 occurs with multiplicity 2 as well. All right? The mode is not both, but which one occurs most frequently. So in this case, even though 7 occurs more than once, our mode here is only 4. In this last case here, I have 2 3s, 2 9s. That's an 11 and not 2 1s. Okay? All right? So here, this is an example of bimodal data. All right? And so you would report that the modes are 3 and 9. Now, whenever you look at some software and they reports you what a mode is, there may be some indication that data are multimodal, but they may only report one of them to you. It may be the lowest one, it may be the highest one. You have to do a little bit of legwork and figure out what it is. Okay, so just because you have software that can compute some of this stuff doesn't mean it's going to give you everything you need to know.